So far we have seen that using truly random bits, that is bits that are uniformly at random and independent of each other, we can actually generate a lot of uniformly random bits, but bits that are pairwise independent of each other. And this seems very promising, but unless we can make use of these pairwise independent random bits in some way, in some meaningful way, they're not of much value. So in this current segment, we're going to talk about how we can take advantage of these pairwise independent random bits. The first thing that we're going to look into is whether the tail bounds that we have studied so far make any sense in when we consider pairwise random bits. So let's look into that a little bit more carefully. Let's begin with some bad news. Well, if you recall, Chernoff bounds crucially rely on the independence of the individual random variables. And so there's not much hope to get Chernoff bounds to work. But all is not lost because we do have Chebyshev's inequality, and that one doesn't require independence as much as it requires the knowledge of the variance of the random variable. So in this case, with pairwise independence, variance is sufficiently well behaved. And so we should be able to use Chebyshev's inequality. So let's see how that can work. So we're going to try to use Chebyshev's inequality. And for that, let's define x1, x2, and so on up to xn to be pairwise independent random variables. As usual, we are interested in the sum of these random variables, so that is denoted by x. We want to establish that the variance is clean and easy to use. So when we want, now let's look at how to compute the variance of x. And this variance is given by this formula where we first sum over I equals 1 through n variance of each individual xi. But these random variables are not independent of each other, and so we need to actually also add their covariances. So in addition to the initial summation, we will also have to have a second summation over all pairs I and j, the covariance of xi, xj. Now let's look at the covariance term a little bit carefully. What is the covariance of xi, xj? The formula is the expectation of xi minus the expectation of xi times xj minus the expectation of xj. Okay, so let's expand that out. We're going to get this long expression, and if we further, using linearity of expectation, if we take the expectation into each of the terms individually, there's a few cancellations that take place, and we'll be left with e of xi times xj minus e of xi times e of xj. But notice that these random variables xi and xj are pairwise independent, and therefore e of xi times xj will be equal to e of xi times e of xj. So this expression turns out to equal 0. So going back to the formula we had for the variance, we have a summation over the individual variances plus the summation of pairwise covariances. But these pairwise covariances vanish. We just saw that. So what we're left with is that the variance of x is simply the summation of the individual variances. And so this is very nice because now it can be easily applied into the Chebyshev's inequality. So to apply Chebyshev's inequality, we just have to look at the probability that the absolute value of x minus the expectation of x is greater than or equal to some a. and Chebyshev simply tells us that that's at most variance of x divided by a squared. And we have a nice simple formula for the variance of x, so we simply plug that in. So it's nice to see how the Chebyshev's inequality can be applied, and that's nice and theoretically elegant. But let's look at an example where it's actually applied. Let's try to estimate the expectation of a continuous function. Okay, so this is going to be our application. We're going to use fewer random bits, and by that I mean that we will be using fewer independent random bits than normally needed in order to be able to successfully estimate the expectation of a continuous function within reasonable epsilon delta parameters. Here's the function f. It's we're interested in the function in the range 0 to 1. Domain is also 0 to 1, and we assume that the function is continuous and differentiable in the range 0, 1. What we want to do is compute the expectation of f of x, where x is ranging from 0 to 1. And we all know the formula for that is simply the integrating f of x dx from 0 to 1. But we don't know anything about f of x. F of x can be a fairly complicated function. All we know is that it's differentiable and it's continuous. So this expression might not be easy to work with. So we need to estimate this, this quantity. So here's how we do it. We apply two important steps here. Firstly, we discretize the region 0 to 1. And then, even when we discretize it, we get a lot of discrete points, so we really cannot compute f of x in all of those discrete points. Instead, what we do is we subsample from those discrete points and only compute f of x in those subsampled points, and then use that to estimate this integral. Okay, so let's look at it a bit more carefully. So first of all, what we're doing is the first step is discretization. So we have the domain of the function ranging from 0 to 1. We're going to break that up into small pieces, and these pieces can be thought of as being indexed by this variable I. Each discrete point, therefore, is I divided by 2 power n, because there are 2 power n discrete locations. And when we discretize this domain in this fashion, what we can see is that the expectation of f of x is approximately the average value that f takes in all those discrete points. And that's what this formula says. But there's a little bit of care that we need to take. If the function f was to, even though it's differentiable, if it were to fluctuate wildly, then this formula may not work. So what we need to ensure is that the derivative of f, which kind of tells you about how much it, how steep f can go, if we want to ensure that that derivative is bounded by some small constant. So this is an extra assumption that we're making, which is reasonable for most applications. So under that assumption, we get this approximation. But notice that to get this good approximation, we need to have 2 power n discrete points. And that's just way too much and way too expensive. We cannot compute f of x at all of those 2 power n discrete points. So as we mentioned earlier, the trick is to subsample a few of the discrete points and then estimate f in those locations, compute f in those locations, and use that to estimate e of f of x, which we denote by this f bar. So the question is, how many samples do we need? And more importantly, how many independent and uniform random bits do we need in order to be able to get those samples. Let's first approach this using the traditional technique that we know, and that's using Chernoff bounds. And in a context like this, we need to use a slight variation of the usual Chernoff bound that we normally know. So let's state this new Chernoff bound. Here, let's Z1, Z2 up to Zm be independent and identically distributed real-valued random variables. So this, for example, will be used to model the samples that we draw from each of the 2 power n discrete points. But this bound itself is more general. So Z1 to Zm are just IID real-valued variables, and their mean is in the range 0, 1. And each of the Zi's take values from a finite set of values in the range 0, 1. They don't even need to be equally spaced, but in our case, they are equally spaced. Uh, we don't even need that, but we do have that if in the as far as we have this freedom to allow Zi's to take any finite set of values. And now let's look at the probability that the sum of these Zi's deviates far from its mean. Okay, in particular, let's look at the difference between the sum of the Zi's minus m times the mu being the mean of each Zi. What is the probability that the absolute difference between these two terms is more than epsilon m? Well, we get a Chernoff bound here, and that's at most 2 raised to the e, 2 times e raised to the negative 2m epsilon squared. Okay, so this is very nice. So let's it makes life easy. We can apply this directly to our context. We can, in order to get a nice epsilon approximation within a confidence interval of 1 minus delta, what we need to ensure is that the right-hand side of this Chernoff inequality is at most delta. And in order to ensure that the right-hand side is at most delta, all we need to ensure is that the m, basically m is the number of random variables that we considered. In other words, the number of samples that we need must be in big omega of 1 over epsilon squared ln 1 over delta. And each of these samples, remember, these are real valued variables. In our context, they are going to be one of the 2 power n discrete locations. So each of those samples requires n bits. And so the total number of random bits in this approach would be big omega of n over epsilon squared ln 1 over delta, which is quite a bit. So of course we're interested in improving this. So we ask ourselves, can we do better? So our approach, our second approach, will try to improve this, and that's using Chebyshev's inequality. And here we try to exploit the pairwise independence. So let's try, pairwise independent samples. Now we call them x1, x2, and so on up to xm. These are pairwise independent n bit vectors drawn from 0, 1 raised to the n. Now you can interpret these as basically indices in the range 0 to 2 power n minus 1. Now let y be average value of the function f evaluated at each of the discrete locations indicated by these pairwise independent n-bit random variables. So remember, these xj's, we're interpreting them as n bits. They're basically a location, an index into the 2 power n discrete locations. So this xj divided by 2 power n will give you the real value, the value between 0 and 1 that at which we need to evaluate f, and we're evaluating f at that point. And since these xj's are drawn uniformly at random from 0 to 2 power n minus 1, the expectation of y is exactly equal to the f bar, which is the estimate of the expectation that we want. So that's great, but how are we doing on the variance front? Well, variance of y is simply the variance of the right hand side, which is 1 over m summation j equal to 1 to m f of xj divided by 2 raised to the n. And as you all know, when we get a constant from inside the variance and we pull it outside of the variance, it has to get squared. So that's equal to 1 over m squared, variance of whatever is inside the parentheses. Now the variance of this summation we've already seen can be rewritten where the variance is taken into the summation. So this variance that is outside can be taken into the summation, and so we will get summation j equal to 1 to m, the variance of f of xj over 2 power n. But each of these xj values is essentially of the same variance, so we simply, for any fixed j, we multiply the variance by m, and that's what we get over here. And so with some cancellations, we get 1 over m, and then notice that the variance is of a variable x, for example, is equal to e of x squared minus e of x the whole squared. So if we just want an upper bound, we can just use the first term in this formula for the variance. So what we do is replace this variance term with the expectation of the square of the random variable. And by doing so, we will get an upper bound, which is what we care about. But it's clear that this expectation is going to be at most 1. Well, why? Why is that? Because f, remember, is bounded from above by 1 throughout the range of throughout its domain, which is 0 to 1. So this expectation is going to be at most 1, and so we can get an upper bound on the variance, which is just 1 over m. So let's plug that into our Chebyshev's inequality. What is the probability that our random variable y is close to the estimate that we want? In particular, what is the probability that the absolute value of y minus f bar is greater than epsilon? And that Chebyshev's inequality tells us that it's bounded by variance of y divided by epsilon squared. Okay, so if we apply that, remember variance of y is 1 over m, and so we get 1 over m epsilon squared as the upper bound on this on this bad event. And we want this bad event to be at most delta. And this will imply that m has to be more than 1 over delta times epsilon squared. And if you recall, that's more samples than the approach that we took earlier using Chernoff bounds. So in the Chernoff bounds approach, we only needed big omega of 1 over epsilon squared times log 1 over delta. But here the log log is replaced by just 1 over delta. So that seems like a bit of negative news. So how do we interpret this situation? Well, we have to recall that we can generate a lot more samples using fewer bits when all we want is pairwise independent samples. More precisely, if we had 2n uniformly at random and independent random bits, then we saw that we can get 2 power n samples, each of n bits, each n bits long, and these 2 power n samples are guaranteed to be pairwise independent. And if if the number of samples that we need here, 1 over delta epsilon squared, that's just a constant. So we should be able to generate that with very few truly random bits. So in that sense, when our goal is to minimize the number of truly random bits that we need in order to do the sampling, this approach tends to be much better. So let's conclude. What we saw in this segment is that pairwise independent random bits are actually useful. First of all, we saw that tail bounds like Chebyshev's inequality can be applied, although Chernoff bounds cannot be applied. So we win some, we lose some. And moreover, we also looked at an application where the number of truly random bits that we needed was far fewer, even though the number of samples that we took was that we need to take is a little bit more. And that's a significant improvement. In particular, keep in mind that there are some contexts where the number of truly random bits must indeed be kept low. So one reason why this is required is when you run some sort of a scientific experiment, when you need to be able to replicate the sampling. If the number of samples is a lot, you may need to store all of them for replication. But if the actual truly random bits that control these experiments was small, we only need to store those random bits, and then we can, since the pairwise independent random bits were generated via an algorithm, you can actually generate the required pairwise independent random bits and replicate the experiment. And all we needed to do was store very few truly random bits. So that's just one of many reasons why we go through all this rigmarole to ensure that the number of truly random bits is as small as possible. So with that, we conclude this lecture. In the next lecture, which is an extension of the ideas that we have discussed in this lecture, we will extend our ideas of pairwise and k-wise independence to hash functions. So stay tuned for that.